Good morning, Astronomy 1020. After a glitchy beginning to today's lecture, we're ready to begin our 12th week of lecture. Last week, as Vladimir mentioned in the preamble, we learned about special relativity, and we did not quite get to general relativity. However, today we need to get back to stars. Vladimir, I'm going to try to work general relativity into the lectures coming next week. This week, we want to talk about nucleosynthesis, how stars generate different varieties of fusion in their cores, and how that eventually leads them to evolve into more exotic objects, red giants, blue supergiants, and white dwarfs, and eventually even neutron stars and black holes when they enter their death phase. So this lecture that we're about to do loosely follows chapter 17 in the book, okay? And chapter 17 has to do with the subjects that we call nucleosynthesis. Someone's got their situation not muted, and don't make me find you, okay? All right, nucleosynthesis is how stars use fusion to generate elements. The very elements that make up our planet, our bodies, and our pet dogs and squirrels, okay? This chapter is also about the sort of stellar evolution. And stellar evolution means a progression where stars form. We've already covered that. We call the formation of stars protostars. Then they evolve into actual hydrogen to helium fusing stars. We call them main sequence stars. Eventually, they're going to generate different types of fusion. And when they do that, they will evolve into either a red giant or, in very high mass star cases, a blue supergiant. And then they will go into some kind of a death cycle, which will be covered either next week or the week after that. So we covered this subject before relativity in chapter 16. Death will be covered in chapter 18. So today what we're going to focus on is this middle part, how stars become stars, what sort of fusion they do, and how they eventually evolve into red giants or blue supergiants, and what that's all about. So this is the area here of chapter 17. I thought you guys might want to try to understand how this week's lecture fits into the grand scheme of things. So let's remember that although there are many different spectral types for stars, that stars kind of come in one of three categories, one of three mass categories. In fact, since today's lecture is a bit compressed, it might actually make sense for us to kind of develop a chart that will help us think about the material today. So Andy, let me know when you've got all this down, and then I'm going to start making a little chart that covers today's material.
I get it all down.
Okay. What we're going to start off by doing is making a big chart that summarizes all of chapter 17's material. And we're going to list in each box the different sorts of fusion that stars of different varieties do. And as we go through the chart, it'll give us a chance to kind of have little breakaway moments and talk about this stuff. So what I want to do is I want to make a chart with an initial column And the initial column is going to represent the sort of mass type or the mass class of stars. And you guys may remember, or you more likely forgot, that there are 3 different mass ranges for stars. How do I want to do this? We'll do low mass first and high mass second. So there are low mass stars. There are intermediate mass classes of stars. And then there are high mass stars. And we'd like to follow their evolution through several different types of fusion. The very first branch, which we'll put here, hopefully that's enough room for everything. This will be dedicated to the main sequence phase that the stars must all go through after they initially form. Then we will have a sort of red giant phase. In the case of some of the stars, they might actually become a blue supergiant. So we'll leave a little window there. And then eventually the stars will undergo some kind of a death cycle, which depends upon the mass of the star. So these are the things we'd like to cover today. Their main sequence phase, their red giant phase, the blue supergiants for some of them, then a death phase. Here's where I want some class participation. What are the mass ranges of stars in terms of their solar masses, or in terms of the mass of the sun? So here's where it'd be helpful for one of you people to participate in the class and make it feel like this is real for a second. I've got, what do I got? 3 by 4. I've got 11 students here. Someone needs to freaking participate with me, or I'm going to log out and give you the pre-recorded video. Okay? That's not too much for me to ask. I'm quite sure of it. All right, Nick. I need a mass range for stars.
Okay, I was just filling out a chart.
Oh, what do you got, Vladimir? Give it to us.
So the lowest a star can go, I believe, is 10% of one solar mass.
Correct.
And the upper boundary is 100 solar masses.
Oh, okay, that's at the highest range.
Yes.
But what I'm trying to get you to remember is a couple of weeks ago, we categorized stars into one of 3 categories, right? Maybe you guys need a little picture to come.
From 0.1 to what? To 3 solar masses?
2 solar masses, but okay, fine. I accept that. So the picture that we kind of looked at, where's that? We're sort of, where are you bastards? 3 kind of general categories of star, right? Actually, this slide isn't ideal because this presents a 1 solar mass star as an intermediate mass star, but it's actually not. The cutoff is 2 solar masses. So let's change that to 2 solar mass stars. So low, intermediate, and high mass stars. And I showed you that picture before. So there's your low mass star, 1/10 to 2 solar masses. How about the intermediate range? This might be a good time to announce that I'm considering, depending on, you know, how well I think you guys know this stuff, of giving you the option of doubling your midterm grade and opting out of taking the final. But if I were to consider doing that, I'd really want you guys to kind of prove to me that you're learning and understanding some of this stuff. This is something we can talk about next week. There's
2 to
Matthias.
10.
2 to 8 solar mass units.
Ah, okay.
And that means high mass stars go somewhere from 8 to 100 solar mass units. Okay, let's have another test question. What are the spectral types of each of these mass ranges?
Oh, I know.
Okay.
So for the low, it's GKM.
Okay, fine. So let's use symbolic colors. So these are G, K, M. Intermediate mass,
A and F.
A and F. For high mass stars,
And then O and B.
that's right. These are their spectral types when they hit the main sequence. Okay. Let's take a look at the Hertz-Sprung-Russell diagram. Tell me about the quantities that are being plotted on an HR diagram. And if you can't remember, well, then you've got the thing right in front of you and you can just read off the chart. What's plotted on the x-axis and what's plotted on the y-axis of a Hertz-Sprung-Russell diagram?
So the x-axis is temperature, the y-axis is luminosity.
Correct.
In terms of, so luminosity is in terms of solar luminosity.
Sure. That's what we would call a theorist's HR diagram, Vladimir. Temperature is on the x-axis, luminosity is on the y-axis. Observational astronomers, who are kind of the, well, closer to experimentalists, they're the people who collect data, they usually plot color or spectral type versus magnitude. And that's something we're going to have to get into today. When an actual astronomer goes out to try to create an HR diagram, they cannot directly measure the temperature or the luminosities of stars. So they often play a sort of cheating game where first they sort of take several pictures of the star. So I'm going to tell you some real astro lore here. An astronomer goes out with their telescope and they use 3 different filters, a blue filter, a green filter, and a red filter, and they take 3 different images of the star. Each image has a magnitude associated with it, how bright it is, for instance. And you guys will remember that stars, being black bodies, will have different color temperatures depending on how hot they are. So if you have a very high mass, hot star, it will give off more light at the blue end of the spectrum. A star like our sun will give off the most amount of light somewhere in the middle, near the green end of the spectrum. And a low mass star will give off light near the red end of the spectrum. And what they actually do when they create an HR diagram, and I want to show you a real one for just a second here, is they make what's called a color magnitude diagram. Function F562. Oops. They plot on the x-axis the color of the star. Now, they plot it in magnitudes. Remember that the magnitude system is a unitless system for measuring the brightness of stars. And they subtract the blue magnitude, the magnitude in the blue filter, minus the magnitude in the green filter, which for historical reasons, green is called V, for visual band magnitude. So this is basically how blue is your star, measuring blue magnitude minus green magnitude. Let's see what you guys can remember from your magnitude lectures, which should have been a pre-recorded video, and that's giving me the willies because I suspect nobody actually watched it. Class, let's say I take 3 pictures of a star, and the star has a blue magnitude of -1, a green magnitude of 0, and a red magnitude of +1. What does this tell you about the color of the star? This is apparent magnitude, by the way. Remember, little m is apparent magnitude. What does this data tell us about the color of my star? How do magnitudes work? Who watches the videos?
I watched it, but I don't remember you talking about it.
I had to have talked about it. That's an absolute necessity. I made sure that was in the video that I sent to you. So that's just not true.
So you subtract v from b, which leaves you with -1 again.
Right, but that's not going to be
Does
helpful.
that-
Vladimir, we can't talk about b minus v. I realize that I can't tell you what b minus v is if you have no fucking clue what b, v, and r mean. If you don't know what a magnitude is. If a star has an apparent magnitude of -1, what does that mean?
Well, that measures how bright it is.
Right.
It's, I don't know, it's pretty bright. Sun is like, I don't remember,
-27.
Yeah.
But the sun is not a good comparison for stars because stars are so much dimmer. You guys will remember that Hipparchus invented the magnitude system, and he ranked stars by their apparent brightness. The brightest stars were number 1, the second rank bright stars were number 2, and he divided the sky up into 6 magnitudes, right? So the very brightest stars that he could see with his eye, he called a magnitude 1 star. The second brightest stars he called magnitude 2. The third brightest stars he called a magnitude 3. The stars dimmer than that were magnitude 4. But we've since extended his scale because he didn't account for certain stars. The star Vega is even brighter than what he thought were the brightest stars in the sky. The star Vega has a magnitude of 0. And the brightest star in the sky, Sirius, has a magnitude of -1. This is called apparent magnitude. It's going to be in our labs today, and our lab is really going to suck if you guys don't know this. So this is scaring me a little tiny bit. So tell me a little bit about my star. I took a picture of it with blue glass filters, and it had a magnitude of -1. I took a picture of the same star in the green band, and it was a magnitude of 0. I took a picture in the red band, and it was a +1. Maybe you need the cartoon picture. Okay?
Oh, wait. Isn't there like wait. Aren't some of them in decimals too? Like the
Yeah,
magnitude?
you can do decimal fractions. You can have a magnitude of 0.56, but I don't want, if you can't handle the whole numbers, then there's no point in getting into that, you know?
All right.
But you're not wrong, Andy. You're correct.
What is it?
So that measures how much light output and what spectrums the star is emitting.
But all of these measure the amount of light the star is getting, but we're sampling it in different parts of the visual spectrum. The blue filter tells us how bright the star is at blue wavelengths.
Yeah, but like this doesn't make sense because if red has a longer wavelength, right? Then it should be even less. Oh, of course. Wait, it is less than green. Okay.
Okay, so what kind of star am I looking at here? If it has a blue magnitude of -1, a green magnitude of 0, and a red magnitude of +1.
Would you
I'd
be
say-
looking at the biggest one, which is blue?
Well, this star is.
Are you talking about star types like maybe B?
Yeah. So, guys, do you know how they talk about rose-colored glasses? How you could put on some John Lennon glasses that are rose tinted and everything in the world is red? I could do that to the sun. If I looked at the sun with rose-colored glasses, the sun would look red. If I looked at the sun with blue glasses, the sun would look blue. And if I looked at the sun with green glasses, the sun would look green. Because guess what? The sun gives off all the fucking different colors of the rainbow. But the sun would not be equally bright in blue, green, and red.
I kind of got this with like your little picture over here. So
Uh-huh.
so B is -1. So if
So
it's like a positive number, is that a star? What is those?
those
those
numbers rank how bright they are. This means kind of bright, this means brighter, and this means really, really fucking bright. The smaller the magnitude, the brighter the star. It's all upside
All
down.
right, yeah. So
That's
yeah,
Hipparchus's fault. So what can you tell me about this one star that has a -1 blue magnitude, a 0 green magnitude, and a +1 red magnitude?
that one's really bright, but that's not so bright, and that's not really bright.
This is dimmer. Well,
Yeah,
relative to each other. This star gives off
yeah,
more.
they're all stars, but they're all
No,
different in there.
This is one star.
Oh, this is one star.
It's one star, but you're taking a picture of it 3 different times, right?
It gives the most light output in the blue spectrum.
That's right. So let's just backtrack here. You've got a single star, right? You're taking a picture of it 3 times. Once with a blue piece of glass, a blue filter, once with a green piece of glass, and once with a red piece of glass. And that star gives off more blue light, less green light, and the least amount of red light. So that star must be what spectral type, Vladimir? Take a guess.
O or B.
Good.
More like B.
Now, okay, so now I think we're starting to understand. So let's try it again. Now I'm going to take a picture of a second star. This star has okay, so apparent magnitude uses little m when you're just doing it without filters or without colored glass. But when you take a picture of the star multiple times, you use R for the red filter, V for the green filter, and B for the blue filter. So let's make up a new star. This star has a blue magnitude of +2, a green magnitude of 0, and a red magnitude of +1. I don't know, I just made that up, but what would you say about that star?
It's more like our sun.
Very good, Vladimir. Can you explain that to the rest of the class that isn't following you right now?
Since the larger, the more positive numbers, the less light output in that spectrum the star gives off. So B is 2, meaning that the star gives the least amount of light output in the blue spectrum. And
Right.
V is 0, which is the smallest number, which means that that's the biggest light with that spectrum. And R is somewhere in between.
Yeah, but this is a star. This star gives off the maximum light in the green portion of the spectrum, and it gives off slightly less light at blue and red. So most likely the type of star that we're dealing with here is a sun-like star. A sun-like star peaks somewhere in the green portion of the spectrum. So it has the brightest output in green and slightly less in both blue and red, correct? All right. Fine. So now, when an astronomer who's an observationalist who actually goes to the telescope, when they make an HR diagram, look what they're plotting on this axis. This matters because this is part of our lab today. They're plotting the color of a star by subtracting the blue minus the green magnitude. So this is a color measurement by subtracting how much blue light do you get versus green light. Now, why do they choose blue minus green over blue minus red? because it just works better this way. You'll have to trust me. And so the smaller your number is, the bluer your star is. So these would be blue type stars. These would be red type stars. And here they're plotting the absolute magnitude, which is kind of like the luminosity. And sure enough, you'll notice that stars form a classic HR diagram. There are different zones of the HR diagram. This part of the HR diagram is called the main sequence. Do you guys know what this part of the HR diagram is called?
Red and blue supergiants.
No, this is
red
red.
giants.
This is the red giant branch.
Oh, that's right. They're not in the blue. Okay.
Blue supergiants live up here. This is where the blue stars are. And down here are the white dwarfs, okay? So where do we see the greatest number of stars? In which branch do we see the largest number of stars?
Main sequence.
That's right. Let's say, Vladimir, look at all these data points, right? How many stars do you think they sampled here? I'm guessing maybe 1,000 or so.
Sounds reasonable.
So maybe this is 1,000 stars. Of those 1,000 stars, what percentage of it does it look like fell on the main sequence?
Say 97.
Well, maybe like 85 or 90. It looks like maybe 80 to 90% of the stars fell in the main sequence. Maybe 10% as red giants, and a very, very small percentage ended up as blue supergiants or white dwarfs. Most stars, when we see them in the space, they tend to be located in this main sequence branch. And the reason why is because this is where a star spends the greatest amount of its time. Stars that are on that diagonal line, it took us a long time to figure this out. Those stars are undergoing a particular type of fusion, and let's write it down. During the main sequence phase, they are undergoing hydrogen to helium fusion. Sorry. That's the type of nuclear fusion stars are undergoing during their main sequence lifetime. And this type of fusion takes the longest amount of time for a star. So they spend the vast majority of their lives there. Here's something that we should have gotten to during the Protostar lecture, but we sort of didn't. You know, you can plot anything on an HR diagram because an HR diagram is simply a measurement of temperature versus how much light you give off. You could plot a burning log on the HR diagram. You could even plot your pet cat on the HR diagram. How would you do it? You'd measure its temperature. You'd measure the amount of light it gives off. Does your pet cat give off light? Yes or no?
Yeah.
In what waveband does it give off light, Vladimir?
Infrared.
That's right. Your cat is a warm object close to 300 Kelvin, and your cat glows at about 10 microns. And by the way, so do you. Now, unfortunately, you and your pet cat are a lot dimmer than a typical star. Let's go to slide 56. Before stars become stars, they are just big, giant, cold clouds in space. Stars start off as some kind of a giant nebula of cold gas. And that gas is very cold, but it does have a temperature. And that gas barely gives off any light, but it does have a luminosity. If you were to try to plot a cold cloud of gas on an HR diagram, it would be way cooler than a typical star, so way the hell over here. And it would be way dimmer than a typical star, so it would be way down there. As a star turns into a protostar, it goes through several different phases, physical phases of collapse. One where it infalls and turns into a rotating disk with the protostar assembling. It goes, so that's a stage where gravity is collapsing the giant cloud. Then it sort of looks like a star, but it's not quite a star yet because there's no fusion. Then it goes through a period where it sort of churns around through convection, and it's basically turning into a big lava lamp of hot bubbling gas. Then it goes through a period where it ionizes the gas and turns it into a plasma. And then it goes through a very last stage where it actually brings the central core of the star up to the temperature it needs to fuse hydrogen into helium. Do you guys remember what that temperature is?
15 million kelvins.
Right there. That man knows his stuff. 15 million Kelvin is the temperature at which hydrogen will begin to fuse into helium. Vladimir, what's the difference between a star and a protostar? What's the technical difference? Anyone's welcome to answer this question if they think they know the answer. What's the definition of a star?
The core didn't get to 15 million kelvins.
And therefore,
the fusion process was not kicked off yet.
right. So could we all decide that we're going to have a new definition of a star in this class? This is our definition of a star. The definition is ball with fusion. You guys can handle that? That's our
Yeah,
definition.
I like that one better than the first
Yeah.
one.
Ball with fusion, okay? And here's the definition of a protostar. Oops, protostar. The definition of a protostar is a ball without fusion, okay? Protostars actually glow just like stars do. Do you know that when the sun was a protostar, it probably had a greater luminosity than it does today? Yeah.
How is that? Do
Because
they glow like black bodies?
because of the Stefan Boltzmann law for stars. The luminosity of a star is proportional to r squared t to the fourth. The protostar was probably bigger in radius
Oh, I see.
than the star today, and it was wicked freaking hot, Vladimir, because it just formed from gravitational contraction. So it had a whole bunch of high temperature. In fact, look, Vladimir. Look, we know where luminosity and temperature are. On the HR diagram, right? Follow me, Vladimir. When the sun as a protostar was here, it was maybe okay. Maybe it was a teensy bit. Oops. Hold on, let me go to red here and let me clear my drawings. Okay. The sun was maybe a tiny bit cooler than the sun is today. Maybe it was 4,000 Kelvin instead of 6,000 Kelvin. Remember that the radius of a star goes diagonal to the right. The radius of the sun was way bigger, maybe hundreds of times bigger than it is today. So its overall luminosity, as you can see from the diagram, was probably 50 times more brilliant than the sun that it shines today. When the sun was a protostar, it was brighter than it is as a star. Isn't that fucked up? It's about hydrostatic equilibrium. In fact, when the star finally turns on its fusion, when it becomes a star because it's a ball with fusion, what do you see happening to the radius and the temperature of the star?
Wait, what is it? When the sun, when a star contracts from being a protostar?
Yeah.
Oh, so it jumps kind of up and down.
Okay. We better have a little crash course in the HR diagram. See, the one time I asked you guys to watch the video because you weren't willing to participate, it turns out that nobody watched the video. And I kind of knew that was going to happen. Oh, you did? You watched it?
I watched the video, but I don't remember the magnitude part of it either.
It's big time because I really I don't know.
Wait,
I
so you
heard
guys
about-
say I didn't cover the magnitude system? I was
Wait,
almost.
hold on. Did I? What was the last? So the last lecture was the Thursday lecture, and it was still on relativity, wasn't it?
This was like 3 weeks ago, so you guys might be forgiven. Okay, let's talk about an HR diagram.
Oh, I know. I got it.
You plot temperature here.
Yep, temperature, and then the
Luminosity.
ABS magnitude on the side.
All right, but you can also plot radius and mass. The radius of a star increases in this direction, up and to the right. Okay. And if you're on the main sequence only, the mass of a star grows up and to the left. You can get all four properties of a star from the HR diagram, especially if you're on the main sequence. Okay. The question that I was trying to ask Vladimir is, do you see this picture here? I want you to have this cartoon picture in your head, okay? When the sun turned into a star, when the sun was turning into a star, it first started off as a protostar. Do you agree with that statement?
Yeah.
And the protostar went through a couple of different evolutions on the HR diagram. I want to focus on maybe this part of the curve or even maybe this part of the curve. But if you look here and here, at which stage is the star generating fusion? In stage 2 or in stage 4?
4.
That's correct. When the star went from being a protostar to an actual star with fusion, what happened to its luminosity?
It decreased.
Right. What happened to its radius?
Also decreased.
What happened to its temperature?
The surface temperature increased. Yeah.
Very good. Okay, good. Now we're talking to each other. Now we're in dialogue. Vladimir, don't you think that's weird? That when the star kicked off fusion, when it initially turned on its fusion, you would expect, oh, I'm generating energy, so now I'm generating a lot more light. But what happened to the star when it actually kicked off fusion? When it actually ignited its central furnace, the fusion bomb, what happened to its light output?
It lessened.
Why the hell would a star put out less light once it started fusion? I'm having a hard time understanding stars. They're kind of weird. They're sort of counterintuitive.
Can I take a guess?
Yes.
So maybe it's because it's spending so much energy on the fusion and perpetuating it that it doesn't have enough to keep up the light output that it had in the beginning.
That's not good enough, Mateus, because remember, the star is actually going to gain energy. It's going to gain light by turning on fusion. The answer can only be understood, Mateus, in terms of hydrostatic equilibrium, okay? So if I might use this white, I want to keep my chart up on the board here, so I'm kind of doing things a little different today. This is an important question. You first have to understand that this is an issue for me to be able to help you make sense of it all. Before a star collapses, it's not quite in hydrostatic equilibrium. The protostar is a huge ball of gas, right? And the gas is sort of collapsing due to its own gravitational pressure. It's infalling. And as the material's all infalling, the central core is getting hot, right? And it's getting hotter and hotter and hotter as it squeezes. Eventually, the star squeezes down to a minimum radius. Let's use yellow since the sun is kind of yellow. And when the sun gets to like here, it squeezes the central temperature enough for fusion to ignite. But then the star kind of comes into balance, hydrostatic equilibrium, where the gravitational pressure pulling down is balanced by the fusion kicking back out. But you'll notice, Mateus, that the radius has decreased. The Stefan Boltzmann law for stars tells us that the luminosity of a star depends upon two factors, the radius and the temperature. And yes, it depends upon temperature to the fourth power and the radius to the second power, which artificially makes it look like temperature matters more. But the change in temperature is actually kind of small. it's 4,000 Kelvin versus 6,000 Kelvin, which is a factor of a teensy weensy bit. But the change in radius could go from 100 times the radius of the sun down to 1 solar radii, a factor of 100, right? So if you do 100 squared times 0.7 to the 4th power, the 100 squared matters so much more. In other words, the reason why the star both shrinks and drops in brightness is it's squeezing itself down into the balance equilibrium point. Did that make some kind of sense?
Yeah.
Okay. The correct answer to understand this is hydrostatic equilibrium. All right. Let's talk about the day that the sun lands right there. How long ago did the sun plop down on the main sequence in an HR diagram? In other words, how old is it?
4.5 billion years ago.
Correct, 4.6 billion years ago, but who's counting? Okay, fine. So on that day, the sun was called a ZAMS star. This is a concept in astronomy. Zero age main sequence. Our sun today is not a zero age main sequence star because it's been fusing on the old fusion train for 5 billion years. And it will be fusing for another 5 billion years before it turns into a red giant. But stars, the day they are born, they land somewhere on the main sequence, and they are called ZAMS stars. It's a concept for saying it's the first day of a star's life as a star. And what's our definition of star, Andy?
Ball with fusion.
That's right. Stars are ZAM stars when they become a star, when they become ball with fusion. Right. Okay.
Wait, so it's zero age. M is
Main sequence.
Oh, okay.
Because we consider, let's look at an HR diagram for a sec. There's a lot of stuff that you guys have to learn today. It's not easy. When a star lands on the main sequence, it's going to go through its initial method of fusion. And all of the stars, what all of these stars have in common here along this diagonal line, all the stars there are undergoing a particular type of fusion, hydrogen to helium fusion. You guys have already studied hydrogen to helium fusion in the sun. What was the name of the nuclear reaction sequence that a star like the sun will use when it undergoes fusion? This day has gotten mega screwed up, but in a way, I'm kind of prepping you for the lab today, which is also going to kind of suck. What do we call the nuclear reaction sequence by which the sun generates energy by fusing hydrogen into helium? And yes, I do want you to look in your notes to find this. Guys, I'm going to be asking like 1 million test questions about this stuff on the final, so I fear for you. Unless you take my escape hatch, which you probably should.
What's the question again?
There are many different nuclear reaction cycles. You know how like in chemistry, there are different chemical reactions? Well, the sun undergoes hydrogen to helium fusion by a particular nuclear reaction, and we studied it. It has 3 steps.
It starts off with deuterium.
Deuterium is involved in it.
It starts off with 2 ionized hydrogen atoms.
That's right. In the first step, 2 protons collide. They create deuterium.
Create deuterium, and then 2 deuteriums collide, creating helium.
But you don't remember the name of that reaction, huh?
No, I'm trying to find it.
I thought someone out there might be able to find it.
Is it 3 steps of proton-proton chain?
Nicely done, Andy. The proton-proton chain. Clearly, y'all having some trouble remembering this, although Vladimir did kind of have the basic gist. So let's take a peek here in my little window, okay? Because there's a lot for us to remember. The proton-proton chain proceeded by way of 3 steps. In step 1, Vladimir referred to them as 2 ionized hydrogens, and that's correct. But, ultimately, they are 2 protons. They collided to make a deuteron and kicked off a positron and a neutrino. Don't worry about those things. The deuteron collides with another hydrogen to make helium-3 plus 1 gamma ray. And then step 1 and 2 happen twice so that you generate 2 helium-3 nuclei. And then the 2 helium-3 nuclei merge together to make a proper helium-4 nucleus and kick off 2 protons. You might think of them as the 2 protons that showed up here. The overall effect of the proton-proton chain, the so-called net reaction, which I expect you to memorize, is that 1, 2, 3, 4 hydrogens, and remember, a proton is just a hydrogen nucleus, as Vladimir reminds us, 4 hydrogens sort of eventually slam together to make 1 helium nucleus and 1, 2 gamma rays. This is the essence of the proton-proton chain. This is how low-mass stars, like our sun, generate nuclear fusion. Not all stars use the proton-proton chain. So here's where we eventually get into the nitty-gritty of things. A low-mass star uses, now, I didn't make this up. People abbreviate the proton-proton chain as the PP chain. Okay, you can't make this stuff up. So the proton-proton chain is the nuclear reaction cycle that low-mass stars use. And it's 4 hydrogens. I should have left a little more room. Turn into 1 helium and 2 gamma rays, okay? Intermediate mass stars. Stars over 2 solar masses, intermediate and high mass stars, do not use the proton-proton chain to undergo nuclear fusion. They use a slightly different reaction known as the CNO cycle. Because there's going to be several different nuclear reaction lessons or reactions to memorize, I'm going to kind of go easy on you guys, and I'm going to demand that you know the details of the proton-proton chain, and I'm going to demand that you know the names of the other reaction sequences, but I won't make you memorize those details with the same level of specificity. Okay, let's take a look at the CNO cycle anyways, so we can understand how it differs from the proton-proton chain. So let's say you're a more massive star, like a spectral type A or F or O or B. You still fuse hydrogen to helium inside of your core, but your core has a much higher temperature, and at higher temperatures, there are more efficient ways to fuse hydrogen into helium. Let's take a look at them and tiptoe our way through the world of nuclear physics. Okay, you guys know the basic composition of a star, right? Assume all stars basically have the same composition. That means they have the same composition as the sun. What is the composition of the sun by mass? What chemical elements is it made out of?
70% hydrogen and 28% helium.
And what else?
And the metals like carbon and
right.
Nitrogen.
And metals make up a little smattering, 2%, right? Now, somewhere in the core of a high mass star, there's a small amount of metals, maybe a little tiny bit of carbon grit. And even though that carbon grit is super, super low abundance, it actually kind of adds You know how like salt can change the temperature of boiling water so you can cook your pasta? Sometimes a little sprinkle of stuff can totally change the nuclear chemistry of things. Even though carbon is just a tiny bit of salt, that tiny bit of carbon salt actually changes the way stars undergo nuclear fusion. It turns out it's easier to fuse hydrogen into helium by basically using carbon as a sticking pad to glue your hydrogens together. And this is more efficient than the proton-proton chain, provided one, you have some salt, and provided, which most stars do, and two, provided you have higher temperatures. So somewhere in the core of a massive star, there's a little bit of carbon. A hydrogen at a high-speed collision slams into it, sticks to the carbon, and transforms it into a nitrogen-13 isotope. It kicks off a gamma ray and releases some energy. Now, nitrogen-13 is an unstable isotope because it has one too many protons and not enough neutrons to glue it together. Something weird happens. It's called they call it beta decay, and it's related to the weak nuclear force. One of the protons spontaneously pops and turns into a neutron, and it does so by kicking out some antimatter positrons and neutrinos. So literally, it undergoes a random mutation where a single proton transforms itself into a neutron. Because the number of protons determine your element, you're no longer nitrogen-13. You're now an isotope of carbon called carbon-13. Now carbon-13 gets whacked with another hydrogen. It becomes a proper nitrogen-14 nucleus, and it emits a gamma ray. Nitrogen-14 is stable, but who gives a shit? Because it's quickly going to get whacked with another hydrogen, another proton. That sticks temporarily and creates an oxygen-15 isotope, which is unstable, emits yet another gamma ray. Oxygen-15 is pissed off because it has one more proton than it would like and not enough neutrons. The stable isotope of oxygen is oxygen-16, 8 protons and 8 neutrons, right? So oxygen-15 is missing a neutron. So one of the protons gets pissed off. It pops. By beta decay, it emits positrons and neutrinos. It turns into a neutron, and now you have nitrogen-15. Nitrogen-15 gets whacked with a fourth proton. And at this point, nature has two options. When it gets hit with the fourth proton, nature could have actually turned into oxygen-16, a stable oxygen isotope. But instead of doing that, and if you ask me why, I can't tell you the reason. Instead of turning into oxygen-16, nature instead prefers to poop out a helium nucleus and return the original carbon to carbon-12. There is something about helium nuclei that nature loves. Helium nuclei, 2 protons and 2 neutrons, are super, super stable. There's
The
actually,
helium
huh?
Never mind, nothing.
Yeah,
I
I know.
said the helium fetish.
Oh, yeah, okay. So in any case, let's take a look at what happened. Carbon was used during the reaction, but carbon ended up returning to its initial state of carbon-12. In chemistry, we call such a thing a catalyst. It involves and it helps the reaction, but it's ultimately not used up in the reaction. You can keep using it forever. Let's look at the net reaction, and let's even write it down for the C. In fact, the CNO cycle is a bit misleading. It's really about hydrogen to helium fusion, but we call it the carbon-nitrogen-oxygen cycle. That's going to be very confusing for you in a test. When you see CNO cycle, you're going to think it means carbon fusion, nitrogen fusion, oxygen fusion, but it doesn't. It means 4 hydrogens fused to make 1 helium. But look at this. 1, 2, 3 gamma rays are emitted.
Damn.
Let's write that down on our notes.
So the carbon is like a vessel. Like it takes 1 hydrogen, then 2, then 3, and then 4. Like, I cannot take this anymore. Get out of here.
So the cycle is 4 hydrogens fused to make 1 helium plus 3 gamma rays. From your perspective, students, what is the main difference between the proton-proton chain and the CNO cycle?
gives off more energy.
How much more energy? How does the efficiency change going from the proton-proton chain to the CNO cycle?
It increases by
You don't need a calculator.
1.5 times.
So it's an increase in what percent?
50% increase.
That's right. So I can say the CNO cycle gives off 50% more energy.
Yeah, that's huge.
It is huge. It only seems like one lousy gamma ray, but it's one more than two, right?
Yeah, and then considering that this is happening like billions of times per second.
That's the point, Vladimir. It's happening kabillions of times, right? Not billions, kabillions of times per second. There are 10 to the 50 atoms or something inside the core of the sun. And they're all going shitty bonkers. And 50% more energy. In fact, that kind of explains something, doesn't it? It explains, I want to show you guys that picture again. How might that be related to this picture explaining the differences inside the cores of low versus high mass stars? How are the cores of high mass stars different than the cores of low mass stars?
The convection zone is inside rather than closer to the outside.
Or in other words, say it better, Vladimir, the core itself is convective. Why do you think the core of a high mass star is convective?
Yeah, I was sitting and thinking about it. I still don't understand. Like, I remember during the lecture trying to explain. I'll be honest, I don't get it. I didn't
Vladimir,
get it that time.
You're producing 50% more gamma rays inside the core of this star. And photons have momentum. Remember when I pushed the little windmill with photons? If you produce 50% more photons in the core of that star, it'll actually start pushing the plasma and making it turbulent. It's like photon wind that's blowing the plasma around. These low mass stars don't have enough photon production to actually blow
So that's
around.
not happening inside those stars, inside their cores.
In other words, you can see the difference here. These stars are using PP chain, right? They're producing 2 gamma rays. These stars are doing CNO, and with 1 extra gamma ray per reaction, there's so many photons that it's making the core of the star turbulent. It's producing a lot more energy.
Have the turbulent convection zone closer to the outside.
Well, this convection zone here is different. This is about the fact that these stars are so cool that this is all plasma. But at this layer of the star, you actually start to get a significant fraction of neutral gas. And the neutral gas is opaque to the photons. So the photons start heating up the gas and turning it like a bubble. This star is just all plasma. So this is about the fact that the star is now getting so cool that the gas becomes convective rather than being a plasma, right?
There are more lines in the absorption spectrum.
Absorption, something like that.
Okay.
That's the right flavor of the feeling, okay? By the way, if a star produces 50% more energy, that means high mass stars, you know what they're kind of like? They're kind of like Humvees or these other like huge gas guzzling SUVs. They produce more energy, but they use it up a lot faster. So you will remember that when we looked at the time scale for the life cycles of stars, that massive stars like O stars and B stars, they live a lot shorter lifespans than do low mass stars like the sun. The sun might live for 10 billion years, right? But a star like an O star might live 10 to the 7. Let's see, that's 10 times 10 to the 6 years. An O star crunches through its hydrogen fusion so quickly that it burns itself out in 10 million years. If you think about it, guys, what was happening 10 million years ago on Earth? That was still after the dinosaurs died, right? Literally, the blue stars that are in our sky today could not have been the same blue stars in our sky when the dinosaurs walked the Earth. If you went back to dinosaur times, Orion wouldn't have been there in your sky because those stars are big blue stars that aren't going to live very long. Betelgeuse would have been there because Betelgeuse is a weird, If you look at small red stars in the sky, they would have still been there during the dinosaur times. But all the blue stars in our sky today could not have been around 65 million years ago. That's pretty wild to think about, right?
They're just brats.
Yes, they are brats and they go blue.
High energy, and then they die.
Now, because I screwed up today's lecture, I basically lost well, I didn't, first of all, I didn't screw up today's lecture. I screwed up 5 minutes of today's lecture with stuff, and then Zoom and computer glitches screwed up the next 20 minutes. Okay, so it wasn't entirely my fault. So I apologize for that anyways, even though the gods were cruel to me. So I lost a little bit of time today, and today we actually have to do a lab on how stars evolve off the main sequence. So I'll just say a couple of simple words about that, and then we'll take a break and we'll try to go forth as best we can, okay? Eventually there comes a day where the sun is going to run out of hydrogen to fuse into helium. And let's try to take a think about why. Let's go ahead and try to imagine what happens to the sun as it fuses hydrogen into helium. And I want you guys to kind of, how do I want to do this? Why don't we meditate on this picture while I talk about it? Function F575. I need some kind of picture. During the sun's main sequence life, like during the sun's life cycle today, the hydrogen is fusing into helium only in the core. The core is where it's hot enough for hydrogen to fuse into helium. And at first, the hydrogen and the helium are all kind of mixed in together. But let's imagine a hydrogen versus a helium nucleus for a second. And here it might be helpful if I could go ahead and compare these two. A hydrogen nucleus is a single proton, right? A helium nucleus is 2 protons and 2 neutrons. How many times more massive than hydrogen is helium?
So roughly, well, I think you're muted.
Me?
No, Mateus.
Oh, okay.
I'm just guessing. I'm not sure. Is it twice as much?
No.
It's more like 4.
This requires you to know something about protons and neutrons. They have approximately the same mass. A proton and a neutron are roughly the same mass. So if a hydrogen is 1 proton and helium is 1, 2, 3, 4 nucleons, helium is 4 times as massive as hydrogen, right? And the helium nucleus is packed into a super, super small area, just like the hydrogen is. The diameter of a helium nucleus is nothing, okay? Now, consider some other types of densities. Here's a lump of granite rock, right? I got this at Goosewing Beach, and I just thought it was a pleasing stone, so I took it. Granite, or stone, has a density of 3 grams per cubic centimeter. Water has a density of 1 gram per cubic centimeter. So this stone is 3 times as dense as water. What would happen if I threw this stone into a lake?
It would obviously float.
Exactly, because I'm Jesus, okay? I could make granite float on water. Okay, no, I'm not Jesus. Okay, so, or Muhammad or Vishnu, or pick your favorite deity, Odin, okay? Maybe Odin could make it float, but I'm not Odin. And in a normal world where there's no magic, if you're 3 times as dense, a stone will sink to the bottom of a lake. So what's going to happen inside the core of the sun when you start converting a whole bunch of hydrogens into heliums, which are not 3 times as dense, but 4 times as dense? Where's the helium going to go?
Into the center of the core.
The very center of the core, exactly. So eventually what's going to happen to the star, in fact, this is probably already happening today inside the sun. Let's see if we can draw a picture of it. So I want to be careful on how I do this here. So, because I don't want us to get lost. So here's the entire sun. Oops. Let's undo that. Let's make the sun yellow. So here is the entire sun. Now let's go into the core of the sun where it's hot enough for fusion. Here I'll use red just for fun, okay? So here's the core of my sun. That's where hydrogen is fusing into helium, right? But somewhere deep in the heart of the core itself should be a nugget of helium, right? That is growing each day. So let me try to draw in here. So this is a nugget of helium. And helium, by the way, is not fusing inside the sun. It's kind of like a lump of black coal that's inert and not undergoing fusion. And in the outer layers of the core, hydrogen is undergoing the helium fusion, and they sometimes call this helium ash. The helium ash is sinking down into the core of the star. Now, think about it. Each day, each million of years, each billion of years, as the sun generates more and more helium in its core, that helium lump is going to get bigger and bigger and bigger. And eventually there's going to come a day where the entire core is full of helium ash. And on that day, the sun is no longer going to be able to generate fusion because the core is not at 15 million Kelvin. It's not hot enough for helium. Helium fusion requires temperatures of up to 100 million Kelvin. Our sun is just not that hot. But out here, it's too cool for any of the hydrogen to fuse. What's the star going to do on that day when its core is full of helium?
So there's not enough temperature to start the helium fusion, right?
Yeah. So,
meaning that the gravity will start squeezing even more because there's nothing to push out to sustain the
right. But here's, Vladimir, here's where stars don't make 100% sense, because your first time thinking about a star, you forget just how massive and stupidly huge it is. The star actually starts to undergo a kind of schizophrenic meltdown. And this is the last little bit that I need to tell you for today's lesson. You are correct, Vladimir, that gravity will start to squeeze the living shit out of this core because it's not generating any fusion. There's nothing to stop gravity. The star disconnects from hydrostatic equilibrium and the core begins to collapse. But there's a problem with this. The whole star does not collapse. And now let's go over to the slide that I want to show you. Instead of
outer layers expand.
Well, what happens is a little bit awkward. As the core begins to contract, new, fresh hydrogen spills from the outer layers of the star into the contracting core, and that little shell of hydrogen becomes hot enough for fusion. Except it actually temporarily produces even higher temperature fusion rates, and it produces so many gamma rays that the outer layers of the star start to puff out and grow, while the inner core of the star contracts. And this is actually what's happening to Betelgeuse right now. The star is actually disconnected. It's like two stars that are separated from each other. The inner star is infalling, and it can't maintain hydrostatic equilibrium. The outer layers of the star are starting to puff apart. Now, there are some details involved, but eventually this is going to go so nuts, and this disconnect is going to continue on and on and on, that eventually what's going to happen to our sun is this. The core will collapse into a little nugget, and the outer layers will just blow themselves off into a planetary nebula. Now, there are details. Okay? We're going to cover those next time. For now, recognizing that when a star runs out of hydrogen fusion, it will turn into a red giant. And here's what you're going to be doing in today's lab. And this is why I had to kind of go over by a couple of minutes. In today's lab, you're going to estimate how old star clusters are by following stars as they evolve off of the main sequence. And here, this picture will be my final diagram, so just bear with me. Remember, class, that the radius of a star increases diagonally and up and to the right. When the sun turns into a red giant, it will evolve off of the main sequence, and it its radius will begin to grow and the star will march up what astronomers call the asymptotic red giant branch, or just the red giant branch. The star's radius will get bigger, its temperature will get cooler, but what happens to its overall light output?
Oh, it's increasing
Right.
because
Why
the
does
radius is so much bigger.
That's right. The radius is growing so many times bigger, Vladimir, that ultimately it's going to give off more light. In fact, Vladimir, if I can tease you with a slideshow from maybe next week, as the sun undergoes this dramatic change, its radius will swell, probably to the point where our own sun will swallow the planet Mercury, and it will definitely swallow Venus. And there are differing calculations which suggest it actually could swell out to a radius of 1 AU and actually swallow the Earth. But if it doesn't, its radius will become so big that the star will actually brush up against the planet Earth, probably boil our atmosphere away, cook all of the water off of the surface. And on that day, our planet will sort of resemble a gooey, tacky ball of molten lava. And definitely every living organism on it will be dead because the radiation will just cook us to a cinder. So it's not going to be a fun day.
The exciting stuff.
Yes, exactly. That's when the sun and all stars kind of do a phase like that. They'll turn into red giants. Now, on Thursday's class, we'll do the nucleosynthesis of these stages. I at least needed to get you guys to the concept of a swollen star turning into red giants. That's what we're going to do with today's lab. I'll explain all of that in good course. For now, why don't we take some tea break time? It's 1:40. We will continue. We will pick up and do our lab on HR diagrams and main sequence fitting at 1:55. Now, to answer Andrew's question earlier, by the way, thank you so many of you for being live. This makes the fact that I've got 5 of you makes me feel really good about the fact that I did this lecture today. So I'm glad you got here eventually. Let me quickly show you guys what you're going to need for today's lab. Unfortunately, one of the pages, if we were doing this lab in person, I would be giving you this tracing paper. And this tracing paper we're going to place over the top of our HR diagrams. I'll explain it all in a bit. Obviously, you guys don't all have tracing paper to print on. If you do have a printer, try to print this out and see if you can play along with me. If not, you can just kind of follow me. The bare minimum you need is if you guys can at least get this one page, okay? If you guys just want to follow along with me, just print out 15-3, this data sheet, and you can watch me do it and you can copy down the answers. That's how we usually do our cheesy virtual labs, okay? So get that one page if nothing else, or recreate it in your notebooks if you don't have a printer. And then around 1:55 or 2, we'll start this lab, okay? I'll see you guys in a little bit. Over and out. Okay, Astronomy 1020. Welcome to lab number 11. The title of this lab is, that's fine, Tegan. The title of this lab is The Ages and the Distances to Stellar Clusters. This thing that you're going to learn today is some real astro work. It's a technique known to astronomers as main sequence fitting. And I didn't actually learn this technique until I was in graduate school. But it's a cool little exercise because it shows you how astronomers cheat, how they use all these different pieces of their knowledge to try to do some actual astronomy and try to compute the distance to a star cluster to try to figure out how old star clusters are. Unfortunately, this lab is going to be kind of confusing for you guys because you're learning all of the different jigsaw puzzle pieces and you're trying to put them together. And today's lecture is going to actually draw from a lot of different concepts that we've talked about in our class. That means that I'm going to have to say a few words. The actual work that we have to do today doesn't take very long, but the understanding in the concept does. Now, here's the first thing I need to ask Vladimir, Andrew, and anyone else who actually wants to participate. You guys, during the course of today's lecture, gave me some doubts as to whether or not you learned the magnitude system. And today we're going to be working in magnitudes, so it's kind of important that you understand this. Now, my understanding was the videos that I gave you covered the magnitude system. Are you telling me they did not?
Nah, probably just forgot. At this point, I
I
don't
mean, I
even
assume
know.
that you guys had some notes, that you take notes in your notebook.
Like, yeah, I definitely remember you talking about the magnitude system now that I think about it. But like, either I'm super bad at memorizing stuff, or like you never mentioned the filters and stuff.
The filters I usually try to bring up, but it's a small part of the lecture. Okay, so let's do a quick review of magnitudes. All right, so what good is it if I said it or I didn't say it? If no one can remember it, then it's sort of like it never happened, right? Magnitudes are an ancient method of measuring the brightnesses of stars, invented by the Greek Hipparchus. He was considered the greatest of the ancient Greek astronomers. And when we measure star brightnesses in our class, up to now we've measured brightnesses in watts per meter squared. That's a measure of radiant energy, or how much light energy you get from a star. But you don't have to be that sophisticated about it. You can just rank stars, sort of like amihot-or-not.com, by ranking how bright they look to your eye. And that's what apparent magnitude is all about. Hipparchus divided the brightnesses of stars in the sky into 6 different classes. The brightest stars he called a magnitude 1. The second brightest stars he called a magnitude 2. The third brightest stars he called a magnitude 3, 4, 5, and 6. And that was all there was supposed to be to it. Except for thousands of years, people have used this system to keep track of the brightnesses of stars. And it turns out to be kind of useful in its own way. It also turns out to be confusing as hell, because one of the things that Hipparchus wasn't thinking about when he designed this system is he used smaller numbers to represent brighter stars, right? So as we refined this system and learned to use it more, it became grandfathered in that smaller magnitudes would mean brighter stars, and we eventually found brighter stars than Hipparchus was intending. For instance, the star Vega, one of the stars that you can see all throughout the summertime in our sky, Vega has an apparent magnitude of 0. That means it's even brighter than some of the bright stars that Hipparchus was measuring. The brightest star in the sky, Sirius, today has an apparent magnitude of -1. That's the brightest a star gets. You can see that smaller numbers are now getting annoying because we're even getting into the negative class. Technically, the sun is a star, is it not? If you were to measure the apparent magnitude of the sun, it would be a -27. Ah, shit. Magnitudes turn out to be confusing as hell. In addition to magnitudes being confusing for that reason, it turns out there's 2 different types of magnitude. There is apparent magnitude. That's how bright a star looks, okay? And there's absolute magnitude, which is also a measure of star brightness, but it imagines that the stars were all at the same distance. Let me talk about that in a second. First of all, do you guys see here that I have a plot of the stars in Orion? Notice that people even measure magnitudes, as Andrew pointed out during today's lecture. They're not always whole numbers like a magnitude 1 or a magnitude 2. People have gotten into the habit of splitting hairs and measuring magnitudes in between 1 and 2. But you can still kind of round up to kind of get a general sense of it. The 3 stars in the belt of Orion are called Alnitak, Alniam, and Mintaka. Alnitak, Alniam, and Mintaka have slightly different brightnesses, but all of those stars have a magnitude of roughly 2. So they're a second rank brightness. The star Betelgeuse and the star Rigel, they have a magnitude somewhere between 1 and 0. Let's look at an actual picture for a second of Orion so you guys can kind of get a sense of it. It's nice when we actually have outdoor observing in this class, because then I can kind of show you the magnitude system with your own eye, and that kind of helps for it to make some kind of sense. So since I can't actually take you out to the telescopes until we all get vaccinated, What I would do is I would take you out at night and I'd show you Orion and I'd say, here's my way of thinking about it, guys. The stars in the belt, they all have an apparent magnitude of like 2. The stars, Betelgeuse and Sirius, they have a magnitude of about 1 or 0. The stars that make up the bow of Orion, they're probably a magnitude 3. And honestly, do you see all these wicked faint background stars? They would have a magnitude of 5 or 6, but we wouldn't actually be able to see them from CCRI's sky because they're too light polluted. One of the reasons why people are so familiar with the constellation of Orion is basically all of the stars in the majority of the constellation, they're all magnitude 1 or 2 stars. So Orion really pops out against your nighttime sky. Essentially, what apparent magnitude is, it's the same thing as brightness. Unfortunately, today's lab is going to have you understand the concept of absolute magnitude. We use a capital M for that. Absolute magnitude still uses the magnitude system, but it's designed to trace the luminosity of a star rather than its brightness. Now, I probably defined this before, but you guys clearly forgot it all, so we got to do it again. Absolute magnitude is defined this way. It's the magnitude a star would have if you could somehow magically move them to a distance of 10 parsecs, which sounds totally fucking absurd, I know. But it's just a way to say, what would it be like if all stars were the same distance and only their luminosities contributed to their magnitudes? They chose 10 parsecs because it's pretty close to Earth, but it's not. Most stars are a little further away than 10 parsecs. A nice way to think about it, I like to show people this cartoon. Today, the sun has an apparent magnitude of -27 because it's wicked bright in our sky. The famous star Aldebaran, that's in Taurus, it has a magnitude of +1. Let's say you could both move the sun and Aldebaran to 10 parsecs away. Aldebaran would have an absolute magnitude of -1. The sun would have an absolute magnitude, or it does have an absolute magnitude of +5. What does that tell us about the luminosity of the sun versus Aldebaran?
Compared to
Mateus, Vladimir, either one of you.
Oh, okay. So, compared to Aldebaran's, our sun is kind of a weak-ass star.
That's right.
Dim.
That's exactly how I'd put it. The sun is a weak-ass star. It's not very luminous. Aldebaran is thousands of times, or maybe even tens of thousands of times more luminous than the sun. By the way, that's because Aldebaran's a red giant, and it's really, really big and fat, okay? Anyways, now you get it. Absolute magnitude is a tracer of luminosity. Apparent magnitude is a tracer of brightness. All right, here's where we're going to get to today's lecture. In today's lecture, we're going to study star clusters. Do you guys remember in one of those pre-recorded lectures we talked about star clusters? What are the 2 types of star clusters that astronomers like to observe?
Open star clusters and the closed ones.
The globular clusters.
Oh, glob. Okay.
But very good, Vladimir. The Pleiades, which we're going to study today, is a classic example of an open cluster. It has a lot of blue stars in it. Globular clusters have a lot of red stars. They're usually much further away. They're at the edge of the galaxy. Whether an astronomer studies open clusters or globular clusters, star clusters provide a very important tool to study stars. But I'm going to have to walk you through this argument carefully. Let me show it with the whiteboard, okay? Let's say that you're here on Earth, okay? So here's Earth. And now what I want to do is I want to make a star cluster. Let's make it like Pleiades, and it'll be full of blue stars, okay? In a star cluster like Pleiades might have a distance from Earth of like 1,000 light years or something, right? But the stars, separations from each other, they're probably closer to like 1 to 3 or 4 light years apart. So even though it's not perfectly true, it's good enough for government work to say that all the stars in a star cluster are roughly the same distance from Earth. Okay, this star might be 1,001 light years, and this one might be 999 light years. But who gives a shit, because that's only an error of 1 part in 1,000. Do you see my logic? Okay. What's cool about star clusters then is if they're all at the same distance from Earth, I know that any differences in either their brightness or differences in their magnitudes is not really due to their differing distances. It's totally due to their luminosities. So astronomers are great cheaters. In order to study star clusters, what they do is they measure the apparent magnitude of a star. They measure how bright it is. But if they only measure the apparent magnitudes in star clusters, they're actually kind of measuring the luminosities or the absolute magnitudes. Okay, this isn't 10 light years, it's 1,000 light years. So there's some kind of fudge factor there. But measuring difference in brightnesses mean you're measuring differences in luminosities. What that means is you can construct an HR diagram of a star cluster by itself, and it should create a little main sequence and a little red giant branch, just like a typical HR diagram. Let's look at one of those examples, okay? So I want to go to a slide here. Let me just make sure I can find it. The slide for main sequence fitting. It actually might be in a slightly different slideshow, so just hold on a sec. Yeah. It would have been very, okay. I have a better picture somewhere, but okay, I don't love this picture. I have a better one. Let me just figure out where I put it, guys. Just bear with me. It's probably in my stellar. Sorry, too many slideshows up here right now. Let me see if it's. Why? I call this slideshow up every single year. I'm just having a little mental meltdown as to where my best picture is. Maybe it's in here. Oh, it could be that that I grabbed a different slideshow. I have all these different versions of my slideshow, and I'm not sure which ones I grabbed. No, I know it was in this. Is this in the S drive? Aha! Now I see what it is. The more recent one is here. All right, guys, forgive me. I see what I did. I need to close this, and I need to open the one from CCRI, not from my home computer. All right, this ought to fix things. Okay. I'm lost. I can't figure out where the slideshow is. I'm gonna work with this one. Let's say I have 2 star clusters, okay? Function F536. And what I'm gonna do is I'm gonna measure their color, and I'm gonna plot their color or their temperature on the x-axis. And instead of plotting their luminosity, I'm going to plot their apparent magnitude or their relative brightness on the y-axis. First, I plot stars in the Pleiades cluster. Then I plot stars in the Hyades cluster. Instead of seeing one main sequence, I see 2 main sequences for the majority of the stars. Why 2 main sequences? Because these star clusters are at totally different distances. This one might be like 1,000 light years away, right? And this one might be 500 light years away. So what happens is there's really only one main sequence, but all the stars in Hyades are twice as close, so they end up looking way brighter than the other stars. Today's goal is to measure the distance to one star cluster, like Pleiades through parallax, and then we can measure the distances to the other star clusters by shifting and figuring out how many times brighter their main sequence is from the other main sequence. That's one of our goals, okay? Astronomers call this technique main sequence fitting. And it's kind of like building a tree house where you build a platform on one branch and that lets you build a platform to another branch. What happens is astronomers use parallax to find the distance, I believe, to the Hyades cluster, and they know that distance and they can compute the real main sequence. Then what they do is they measure a whole bunch of star clusters. They see a bunch of main sequences that are shifted up or down depending on the brightnesses. They calculate the offset, and that lets them calculate the distance to the other star clusters. So it's kind of like your star cluster hopping based on the fact that all the star clusters will create a main sequence. However, there is a small twist, and the twist is one that I've been preparing for you during the course of today's lecture. Remember that stars undergo different types of nuclear fusion, and because of this, they don't all live for the same lengths of time. O stars tend to live for like 10 million years, A stars live for 1 billion years, and then sun-like stars live for 10 million years, and so forth and so on. Star clusters that we find in the sky, some of them have been sitting around for billions and billions of years. So imagine you had a star cluster that had O stars and B stars and A stars and F stars, and you let it sit around and evolve for millions and millions of years. By the time you eventually go and you actually plot the HR diagram for a star cluster, instead of seeing a normal main sequence, you see something that looks like this. And I want you guys to just examine this HR diagram and think about what's happening. At one time, billions of years ago, this star cluster was full of stars of all the different spectral types. And its main sequence was roughly a diagonal line that shot up like this and was full of stars. But over the years, different spectral types ran out of fusion and turned into red giants. And as you saw in today's lecture, when stars turn into red giants, their radii grow and they drift off of the main sequence and they go up the red giant branch. We can use this fact to date how old a star cluster is. This star cluster, for instance, has what we call a main sequence turnoff point of 10 billion years. And here's the argument. The last star that I see on my HR diagram is roughly a spectral type G star. All the O's, all the B's, all the A's and F's have all turned into red giants. That tells me this star cluster has to be older than 10 million years, because those stars are not on the main sequence anymore. It has to be older than 100 million years, because the B stars are gone. It has to be older than 1 billion years, because the A and the F stars, but it cannot be older than 10 billion years, because the sun-like stars are still on the main sequence. On the other hand, I know that it can't be 100 billion years, because if it was 100 billion years old, I would also see the G stars up here along this branch. Do you see what I mean? So when you look at a whole bunch of star clusters at once, you tend to see a messy picture, and it's messy because real data is messy, that looks like this. This would be a young star cluster because we see the stars turning off somewhere near B stars. So maybe they're 14 million years old. This is a somewhat older star cluster. They're all turning off near the A stars. Maybe it's 1 billion years old. This star cluster has its turn off somewhere near G stars. That cluster is 10 billion years old. And we're going to do that today. We're going to date the ages of some different star clusters. So now you basically know how to do today's lab. I'm going to try to walk us through it. Today's lab is easy to do the work. It's hard to understand the concepts. That's why we had to talk. Okay, let's look at the business of today's lab. I'm going to go into phone mode here, see how this works. Share screen, iPhone. Do it. Zoom. It's connecting. All right, we're connected now. All right, this is our data table. In the beginning of our lab, we're going to focus on calculating something called the distance modulus. I want you to put a star there, just like I did. We're going to calculate the estimated age. I want you to put a star there. And we're also going to focus on something called the color excess, which I'll explain in a moment. These are the first three columns that we're going to focus on. My lab got a little chopped off because it was the last piece of paper in my printer, so don't mind that. Let's put our names. Andrew, you're going to turn in the proper lab to the proper slot today, right, buddy? This is lab number 11.
Yes.
Okay. I've been trying to keep track of it for you, but it's messy. And then don't forget to put astronomy 1020 and maybe even your section, if you can humor me. Whatever your section is, I don't know. All right. All right. Let's take a look at one of our star clusters. And I think I'd like to start today with the Pleiades. Is this the Pleiades? No. The Pleiades would be the first one. You guys may not have printed out all these star clusters to save paper, and that's fine. All you've got to do is kind of look at my page and see what's going on here, okay? Now, do you guys remember what this is down here? I talked about this in today's lecture. What does B minus V mean?
The amount in blue spectrum output minus the output in green spectrum.
Right. So B minus V is like a measure of the blueness or the color of a star. And it's actually measured, believe it or not, in magnitudes, because you measure the blue magnitude and the green magnitude and you're subtracting it. So stars that are over here are wicked blue, like an O-type star. Stars that are over here are red, like an M-type star, okay? Here, you guys are seeing the apparent magnitude, what I called little m in today's training session, but it's the apparent magnitude as measured in the green band, which people usually use because green is in the middle of the visible spectrum. So that's kind of like what your eye would see. Does that make sense? Your eye is more sensitive to green light than it is to blue or red. Okay, and so what we're doing is we're plotting the color versus the apparent magnitude. And sure enough, all of the stars in the Pleiades, they form a diagonal main sequence. And that's because most of the stars are blue stars and other types of stars that this is a very young star cluster. And you can tell because hardly any of the stars have turned off yet. This is not the real main sequence. This is the artificial main sequence because we're plotting apparent magnitude. Remember how we just talked about that? What we're going to be doing is we're going to be comparing it to the theoretical main sequence here on this tracing paper. You guys will notice that on my y-axis here, I have not plotted the apparent magnitude. I've plotted the absolute magnitude in the green band. And that means this is the magnitude a star would have at 10 parsecs, or in other words, this is the same thing as the luminosity of the star, okay? I am going to shift and make the theoretical main sequence match this main sequence. And I'm going to do this in order to measure a quantity that astronomers call the distance modulus. A modulus means an index or a number. Now, the distance modulus in astronomy is like this. It's the apparent magnitude minus the absolute magnitude. And somehow This is actually a measurement of the distance to the star. In other words, what you're doing is you're comparing the brightness of the star to its luminosity. Okay? If these two things are 0, guess what the distance is? You'll never guess. If the apparent magnitude minus the absolute magnitude is 0, take a guess how many parsecs away your star is.
10.
10 parsecs, because that's how we defined absolute magnitude. Okay? Okay. A couple of other things. You guys will see that on the tracing paper, the colors of the star, blue. Oh, by the way, one more thing. Do you guys see the solid line here? That is the theoretical main sequence. What do you think all these little hair-like deedly bobs are coming off of it? What are these little branches referring to?
The ages of star clusters,
These are the
like
so-called
where
the turnoff points is what we call them, Vladimir. These are the main
Yeah.
sequence turnoff points. If stars turn off here, they've got an age of 2 × 10⁷ years or 20 million years. Here it's 50 million years. That's 100 million years, and so forth and so on. Okay. One last thing. Blue minus green corrected index. And on the top, you see blue minus green corrected index. But take a look at the white paper for a second. Blue minus green corrected index. Blue minus green uncorrected index. Why would we need to correct the color estimates of stars? What do you know about? Did you learn about some material that we find out in the disk of the Milky Way that can change and alter the colors of stars? What changes the
the
color?
Doppler shift.
Not the good guess, but the Doppler shifts aren't strong enough to do that here. It's something more
Oh.
profound than the Doppler shift.
Mm.
Something you learned about that's in the interstellar medium that can change the
Because of the interstellar gas.
dust.
Oh.
Gas doesn't change the colors of stars, but dust does. Dust tends to make
Oh, okay, now.
dust makes stars redder than they are. All right. Here's how we're going to do main sequence fitting. There's never any perfect description of this lab. I kind of just have to jump into it, and it's going to suck for a little bit. All right. So let me see if I can balance this phone inside of a roll of tape so you can watch me. I need both of my hands for this job here. Okay. Okay. I've got the Pleiades, and at the top, I've got a corrected index, and at the bottom, an uncorrected index. You guys probably aren't going to do this part, but if you are, I've taken a ruler, and I've done this on this page before, and I've made a vertical line right through the 0 of the corrected index at the top. And you'll see that I've made a vertical line for the 0 of the corrected index on here. The first thing is that I've got to get the colors lined up with each other. So I've got to get the 0 at the top of the tracing paper to match up with the 0 of the star cluster below it. If you look through the tracing paper, you'll see that the Pleiades star cluster has its main sequence here, but my theoretical main sequence is there. Now I've got to keep this vertical line in alignment, and what I'm going to do is I'm going to start to shift upwards until my theoretical main sequence makes a best fit line with my star cluster. Hold on, this kind of requires 2 hands. So let me do the shift, and then I'll show it to you from the above perspective. So I'm pushing the tracing paper up, keeping it vertically aligned. And roughly there. Do you guys see how my theoretical main sequence kind of passes through all the stars in the star cluster? This is called a main sequence fitting. I can use main sequence fitting to calculate the distance modulus. Now, I could take the absolute magnitude and the apparent magnitude at any point along this scale, and if I subtract them, I will get the distance modulus. But here I'm going to try to be smart rather than being stupid. I am going to look at the point where the absolute magnitude is 0. And in that case, the distance modulus will be the apparent magnitude minus 0, or just the apparent magnitude. So notice there's a horizontal line going through the 0 of my absolute magnitude. And you can see it's basically cutting through. Let's cheat a little bit, and let's say it's that tick mark there. That tick mark is this one here. What is the apparent magnitude of that tick mark? That's 4.
Like,
That's 6. What's halfway in between?
5, so 5. So 5.5.
5.5. So in other words, my distance modulus there is 5.5 minus 0. That's my distance modulus, 5.5 magnitudes. Let's record that for the Pleiades. Under the distance modulus, we've just measured 5.5. Now, later on, we're going to convert that into a distance, okay? But for now, we're just going to leave it as a distance modulus. Let's now see if we can track the age of the star cluster by looking for its main sequence turnoff. Okay, for this, I'm going to have to do my fit again because I accidentally pushed the tracing paper. So I've got my best fit there. This requires a little bit of artistry to understand. Now, can you guys clearly see that I have stars all along the main sequence there? None of those would be appropriate turnoff points. By the time I get up here, there are no stars left on the main sequence. I need to try to figure out where they're turning off. And I don't know about you guys, but I can see some stars in the main sequence there, but doesn't it kind of look like there's stars there too, and there's some stars here, but it kind of looks like the greatest number of them are going up that branch. You see what I mean there?
Yeah, kind of.
This can be confusing because the problem is, Vladimir, that stars have slightly different distances and slightly different ages. They didn't all form at the same time. So there's a lot of noise in the data. For instance, you can see 1, 2, 3, 4 stars that seem to be connected to this branch, right?
Yeah, so I'd probably think this is the turnoff point.
I would say that there are more stars on this branch, 1, 2, 3, 4, 5, 6, 7, 8. So I would go with 2 times 10 to the 8. But Vladimir, I do not know if this is more correct or this is more correct. This is where the art of being a scientist comes in. You've got to take your best judgment of the measurement. Since you guys are training with me right now, what do you say we all go with 2 times 10 to the 8? And I'll let you guys choose in the future, okay? So our estimated age is 2 times 10 to the 8 years. We don't have to worry about units because they've got the units in years up there. Now we're going to attempt to get the color excess. The color excess is the difference between the corrected and the uncorrected blue minus green index. Now, I've lined up the 0 of the corrected index here with the 0 of the corrected index there. And I follow this line down to where it says uncorrected index, but weirdly, the 0 of my corrected index is actually lining up with the 0.0 of the uncorrected index. So there's actually no color shift due to dust. You want to take a guess why that is for the Pleiades? It's a lot closer to us than other star clusters, so there's not enough column of dust in our way to significantly affect the color. Pleiades is a weird example of a star cluster that doesn't have any dust affecting the color of the stars. We're not going to do all these, but we'll do a couple more. Let's try doing NGC 6791 for variety. Here we go. Here's NGC 6791. And just like real star clusters, it's a fucking mess, okay? Instead of the beautiful, simple, linear main sequence that you were taught about in your Astronomy 101 class, lo and behold, you go out into the real world and shit is messy because these stars probably have a spread of distances and a spread of ages. There's noise. However, there's kind of a diagonal line like so, right? And you can kind of see the red giants turning off like this. It's not pretty. Let's first draw a line from the corrected to the uncorrected index. That's actually a faster way to measure the color index here. You can see that 0 for the corrected index, in this case, lines up with, what is that number there?
0.2.
So we already know what our color excess is for NGC 6791. It's 0.2. That tells me that dust has caused some amount of reddening for these stars. Let's get the distance modulus, which is the distance and the estimated age. Okay. I line up the 0 of my corrected index with the 0 of my corrected index. Ooh. Normally you start with the 2 zeros on top of each other. You can see my theoretical main sequence sits somewhere below that main sequence. So what I'm going to do is I'm going to slide it up carefully, keeping the indexes lined up. I'm going to slide it up until that line sits kind of in the middle of my star cluster. Can you see that? Okay. Let's first estimate our distance modulus. This is the apparent magnitude of 0. You're supposed to look through the tracing paper to get the apparent magnitude. Can you guys see that? That's
13.75.
Something like that. So let's not go to that 100th place. Let's say this is 13.5. That's 14. 13.5, 13.6, 13. Pick 13.7 or 13.8. What do you think, Vladimir?
8.
Okay. So
yeah, let's go with 8.
all right, sure. You understand what I mean? Like, how do you know it's 13.75 and not 13.76? I don't think you really have that extra digit.
Because it's in the middle of no, because it's in the middle of the middle.
No, F you, man. Look, here's 13.5. Here's 14.0. And you're saying, oh, Brendan, it's in the middle. And so you assume it's exactly in the middle. But look, dude, here's 13.75. And there's 13.76. You mean to tell me that you were differentiating between? What about 13.74? You just picked 13.75 because it's a lucky magic number. You basically might as well be smoking weed and worshiping astrology crystals if you're pretending like you know that number is 5 for certes. You just made that up because it seemed good. Because you like the fact that it's right in the middle, don't you? You like those nice even numbers. No way. Okay.
Yeah,
so,
I did.
All right.
I did. All right.
13.8. Okay. All right. Now, what do you guys think about the turnoff point, the estimated age? Why don't you guys do that one without me? You're muted, Mateus. Oh, he's mumbling to himself. Mateus, I still got to do your letter of recommendation. Don't let me forget about that, okay?
Thank you. Yes, I can show you another email.
Yes, please, 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 right after class or now, whatever.
All right.
What's my estimated turnoff point, guys?
So it's close to 5 times 10 to the 9th.
So want to just go with that? We'll keep it simple.
Yeah, sure.
Right. How many years is that in plain English?
5 billion years.
A lot older than the 20 million years of this cluster. All right. Let's do a couple more. Let's try 6705. I'd like to get at least to Persepe, which is known as the beehive cluster. 6705 is right underneath me. You'll notice I've already drawn a line there, okay? Actually, let's get the color index at first. This is the corrected index. This is the uncorrected index. Kind of looks like right on the money 0.4, right? So over here for 6705, we have a color index, a color excess of 0.4. All right, now let's try to do our main sequence fit, okay? Drag it down, drag it down, drag it down. We're calculating our distance modulus, that's what we're doing. But first we have to make sure that the observed main sequence lines up with the theoretical main sequence. All right. I would say, to my best judgment, that that line is sort of in the middle of the stars. What would you guys say your distance modulus is? So we're going to look at the 0, and we're going to try to figure out what's underneath there. 11, 13.
So that's
12.75.
I wouldn't say 12 point. Once again, Mateus, you're loving those 0.5s, the 0.05. But hold on, Mateus, you've made a bigger screw up than you think. This is 11. That's 13. This is halfway in between, which is 12. So what's this?
Okay.
12.5, not 12.75, right, Mateus? Okay.
Yes.
Right. We have, oops, sorry. $12.5 for our distance modulus. Let's see if we can get that turn off there. Ooh. That was our fit. All right, this requires some judgment. What do you guys think is the best estimated age for this star cluster?
3 times 10 to the 8th.
Oh, you're saying that it's like a little bit in between, the stars are a little bit below this branch?
Yeah.
Oh, that's kind of cute.
Yeah, kind of. Do you think it's like a good estimate or what?
The only reason I'm going to go with 2 times 10 to the 8 is, do you see how we still see some stars on the main sequence there?
Yeah.
If anything, it's, well, this is a messy business. You can't be too precise using, we're getting a very rough estimate, like an order of 10 magnitude. So honestly, I like your daring do. I like the fact that you tried to interpolate between those two. The only reason why I'm not comfortable with it is I can still see some stars here. I was debating between these two. If anything, it might be more like 1 point. Let's just go with 2 times 10 to the 8, okay? Although you didn't want to do a crazy thing there. You did a very reasonable thing. And let me just check how we're doing on time here. Let's see if we can squeeze one more in, and then there's a couple other little parts to this. What's our, can you guys give me the time right now?
It's 2:51.
Okay. So we'll do one more and then we'll finish. We're just going to do these 4. We're not going to do the whole thing because it kind of took a while to explain. But I think if we do these 4, we're going to get the big picture. You know, we don't need to do it 10 times. So let's do the last one here. M44 Persepe is a beautiful star cluster that I know well. It's called the Beehive. If you ever come to my telescope, I'll show it to you. The Beehive is beautiful because it's this big open cluster full of yellowy stars. And when you look through the eyepiece, they kind of look like bees on black velvet. I think that's why they call it the Beehive. I'm not really sure. Beautiful star cluster, a classic for amateur astronomers to see. Its official name is Persepe or M44. We need to kind of draw a line to connect our corrected to our uncorrected index. So I'll use the tape and I'll do that now. You guys will notice that Persepe's uncorrected color index is kind of the same as its colored index, or uncorrected and corrected are the same. It's a very close star cluster to Earth, so there isn't a lot of dust. So it has a color excess of 0.0. Now let's try to do the main sequence fitting to measure its distance. So we're going to expect that both Pleiades and the Beehive are going to be close to us. I expect that these have a lot of dust. They're going to be a little bit further away. Okay, so I've matched up my color indexes. I'm slid until I get a pretty good best fit line. Not all the stars are on it, but they're pretty close. Let's grab our distance modulus here. Oh, sorry. So it looks like our distance modulus is pretty wicked close to 6.0. So let's just take it. What would you guys say the estimated age is?
So if we want to keep things simple, it'd be like 8 times 10 to the 8th.
Yeah. Okay. All right. Let's talk about what we're going to do at first. Let's forget about the color excess. Our first job is going to be to take the distance modulus and to convert it into a distance in parsecs. Now, there is an old classic astronomy formula for this, but we're not going to do the math. I think it's something like this. The distance to your star in parsecs is like 10. Hold on, let me find that formula again. I vaguely know what it is, but I don't want to screw it up. Where do I talk about the distance modulus here? Hold on a second, students. I really should have this memorized, but I don't use it every day these days. Distance modulus. I want the damn formula. I've written down one of my slideshows. Okay. The distance modulus, it's 10 raised to the power of the distance modulus. So there's the distance modulus plus 5 magnitudes divided by 5 magnitudes. So it's 10 raised to all that power. Do you see how that formula is a little bit annoying? I could make us plug in the distance modulus and thereby get the distance. But the idea that the makers of this lab had is that a more elegant way to do it is for us to make a logarithmic plot, and that's the last page of the lab, where they have a graph showing you a best fit line that connects the distance modulus on the x-axis to the distance in parsecs here. Unfortunately, this is a logarithmic scaled graph, and you guys might not have too much familiarity with that, but this is an opportunity for us to learn how these things work, because you do encounter them in science all the time. In a logarithmic scale graph, you don't plot the number itself, you plot the power of the number. So instead of plotting 1, 100, 10, 1000, you're plotting like 0, 1, 2, 3, because 10 to the 0 is 1, 10 to the 1 is 10. The cool thing about logarithmic graphs is by plotting the power of 10, you can change your scale wicked fast, where otherwise, if you did it linearly, you'd need a humongous piece of paper to get from 1 to 1000. So let me walk you through how this works. anytime you want to figure out what each little box is worth, you basically take the interval and you divide it by the number of boxes. For instance, let's look here. There's about 20 boxes between 100 parsecs and 200 parsecs. So if the interval is 100 parsecs divided by 20 boxes, each box is worth 5 parsecs, okay? On the other hand, up here, the scale is going to change. Here it's 10 boxes, right? So 100 parsecs divided by 10 boxes, each tick mark here is 10 parsecs per box. So we're just going to have to take a moment to keep track of this. Let's compute and go from our distance modulus to our distance in parsecs. Our first one for the Pleiades is 5.5. And because I've done this lab on this graph before, you can see that's 5, that's 6, 5.2, 5.4, 5.5 kind of goes up to the line there, and then it goes over. What would you guys say that value is there?
125 parsecs.
Right, 100, 105, 110, 15, 20, 125. Let's do the next one, 13.8. So here's 13 and there's 14. This is going to get really annoying here to do on the phone. Here's 13.8. I'm going to actually sort of use my ruler to guide me. It's important that we do not drift, and it's very easy to drift. It looks like 13.8 intersects right about there. So it's above the dark line. Oops, let's see. That dark line was there, so basically this is where we're at. Now let's see, this is 1,000 parsecs divided by 10 boxes. So each box is 100 parsecs. So what would you guys say that tick mark there is?
3,400.
I would say 3,600. Because look, not this one, Mateus,
Yeah.
but that dark line is 3,000, right? That's a pencil mark. That's
Oh,
what-
okay, got it.
So that's 3,600. So you were counting from my pencil mark. So 3,600 parsecs. Let's try 12.5. It looks like I've already done 12.5. 12.5 is in the middle. So I go all the crapping way up here. Look how I drifted a little bit. If you drift back, that's my dude. And we go over. What's that one?
That'd be 3,200 parsecs.
Excellent, Andy. Here, magnitude, distance modulus of 6.0. 6 is here. We go up to the line. Let's say it hits there. Try not to drift, try not to drift, try not to drift, try not to drift. Boom. In this zone, everything is 5 parsecs per box. 125, 130, 135, 140, 145, 150, 155, 160. All right, we're almost but not quite done. I have one last astronomy related story to tell you, and it won't take very long. In the past, astronomers figured this technique out, and they realized that if they were willing to only study star clusters, they could then use the main sequences of star clusters as a method of finding the distances. And they got all hopped up and excited. And sure enough, what they did is, if this is Earth, they started looking for little clusters of stars all over the place, right? And they began calculating the distances to them. So they used main sequence technique. They found a star cluster there. And they found a star cluster there. And they found a star cluster there. And they started calculating the distances, and they were using them as kind of beacon points to measure reference other distances. The thing that really scared the willies out of them is as they started doing this, right, it looked like all the star clusters were distributed around Earth, and that Earth was the center of the galaxy. Now, they'd already been burned by this once before with Copernicus, and they thought that Earth was the center of the solar system, but it turned out it was just one rock going around a big fat star. Now, what are the chances out of all these thousands and millions of stars that we just happen, in fact, the galaxy contains 100 million stars. The probability that we happen to live on the one star that's at the center of the galaxy is a probability of 1 part in 100 million. In other words, they knew this couldn't be right.
Wait, isn't it like 100 billion?
100
No?
billion. Sorry, I might have said million. I apologize. They were trying to figure out what they had done wrong. And they realized at some point that the interstellar medium contains obscuring dust that was not easy to see, but could potentially affect the colors and the distances to stars. And they started realizing, holy crap, we've been looking through a big field of dust, and this is why things are getting weird. So they came up with techniques to measure the color excess, or the amount of dust that was along the column. Let's turn this into an absorption factor. Let's multiply all of these by 3. 0 times 3 is 0.0. 2 times 3 is 0.6. 4 times 3 is 12, or 1.2. 0 times 3 is 0. These star clusters did not have any dust. Their distance moduli weren't affected. These star clusters did have dust in the way. Their distance moduli were affected. Now let's get a corrected distance modulus by subtracting the original distance modulus minus the absorption in magnitudes. So 5.5 minus 0 is 5.5. Sorry, focus issues here. 13.8 minus 0.6 is 13.2. 12.5 minus 1.2 is 11.3. Correct me if I screwed any of that up, Vladimir. I need your arithmetic. And then 6 minus 0 is still 6. Now, the star clusters Pleiades and the star clusters Persepae did not have any change to their distance modulus, so they're kind of nearby star clusters and their distances didn't change. It's still 125 parsecs to Pleiades. It's still 160 parsecs to the Beehive. But these star clusters, NGC 6791 and NGC 6705, these are globular clusters. And these globular clusters, which are a bit older, they have some dust in between us. 13.2, let's calculate the change in distance. This is 13.2, right? Sorry, I'm screwing up here. Let's go up to 13, and that's 13.2. Which one do I want to go with? Let's go with this guy. Okay. 4,100, 4,200, 4,300, 4,400. We thought it was 3,600 parsecs away, but it was actually much farther away, 4,400 parsecs. And that was because we were bamboozled by dust, correct? Now let's
Wait, I don't understand. How does that work? Because like,
Sure.
I thought that if the number gets bigger, the distance increases and if the number gets smaller, like
But
the
you're
distance modulus.
once again, Vladimir, you're getting fucked up by magnitudes. Magnitudes are all upside down. Smaller magnitudes are brighter stars. That is,
Yeah. Wait, but then how is 12.5 3200 parsecs away and 13.8 is 3600 parsecs away?
basically,
Wait, can you zoom out for a minute?
I'm
I'm trying to.
I'm not quite done, Andrew. I still have one more box to do. Vladimir, these stars are brighter than we thought they were because they were being hidden by dust. The brighter stars basically means they're okay, Vladimir.
Oh, actually, no, I got it. Never mind. Don't bother.
Okay, why don't you share it? Because now I'm getting screwed up too. If the stars, we're comparing it. So the thing that's tricky is we're comparing it to a reference distance modulus that's probably based on the Hyades cluster. This tracing paper is probably based on the Hyades cluster. Whatever. I'm sure everyone wants to just be put out of their misery. Let's calculate 11.3 and let's see what we can get. So 11.3 is just past 11.2. Oh, sorry, that was 13.2. So 11.3 is here. I've already traced the line up for us, which is convenient. And the line goes to over here. Each of these are 500, not 1,000, but 500 parsecs per box. So this is, sorry, these are 50 parsecs per box, excuse me. So this is 1950, 1900, 1850 parsecs. Wait a minute, something got screwed up here. 13.8 should be farther away. Okay. You know what we did, Vladimir? The reason why you got confused is because we screwed up. 13.8 should have a farther distance than 13.2. I suspect that because I'm trying to do this through my phone, I looked away for a second and I got messed up. So there's 13, there's 13.2, and that is 4,400. 13.8. This is 14. 13.8 intersects here. And that's going to be really careful here. That's 2 tick marks below. Okay, the problem, Vladimir, why we both got screwed up is I made a mistake earlier. 5,800 should have been the distance to NGC 6791 before correcting. Deep apologies.
Oh, okay.
In both cases,
Oh, okay. So now it's clear.
the smaller magnitude means the stars are brighter than we thought they were, and that means they're actually closer than we thought they were. The moral of the story goes is once we started correcting for dust, the distribution of star clusters started to look more like this. We were located here on Earth or the sun, and the star clusters were all being distributed like this throughout a spiral galaxy in which we were located in one of the outer spiral arms. This is how we figured out where we are. And it was all really about dust. It was about correcting for the colors related to dust. So famous story in astronomy. Andy wanted to see the whole thing. Let's see if I can go into sideways view for a second. I don't have a lock on this. So this is what we're going to turn in. I know it was kind of a long journey, but it took about an hour. Oops, sorry. Come on. There we go. So this should be our final work, right? And we're going to ignore the rest of this. Those we're not doing. Obviously, it would have taken us another hour to get through all of that, and I don't think you guys, I don't think any of us have that in us. You guys cool? You got that?
Yeah, I got it.
All right. All right, guys. How are we doing on time? I lost my phone's not around.
It's 15:13.
All right. So it took us a little over an hour to do today's lab. There was a lot of yapping involved, okay? Thanks for playing with me. Thanks for learning about stars. On Thursday's class, we will learn more about nuclear fusion, about what happens to stars when they turn into red giants. We will do a hopefully short and painless homework. And then I think maybe we've got, do we have 1 or 2 more weeks of lecture? Where are we at right now?
2 weeks.
Vladimir, you absolutely may have a word with me after class. Let's, before I let everyone go though, can we just take a consensus on where we are? Because it's gotten confusing for me too. When the exam comes up, is this the class where I talked about maybe doubling the midterm, or did I talk about it in the other class? I can't remember.
You talked about it today.
Yeah, I talked about it today. We are currently at 413. So we're not quite at stellar death. We actually did things a little bit wonky in this class. I did relativity here and well, actually, relativity was still pegged to this date, but I'm behind by a week. So today's lecture is there, stellar death. I might be able to do a little bit on the Milky Way, but I'm probably also going to include some general relativity. It might take a little bit of time to get through this. So we got a couple of weeks left, next week and the week after that. When the final exam comes, I still need to I have my final exam created, but I need to load all the questions into Blackboard, and it's honestly a miserable experience. It's going to take me like 3 days to do that, and I have to do it for both of my classes. I still need to do it at some point, so I should kind of get on it anyways. But I am open if you guys are feeling stressed out at the end of the semester. If you're willing to just take your midterm grade and double it, basically use your midterm grade in place of your final. Most people kind of score somewhere around their midterm grade on their final, plus a few points, you know. Not everyone, but most people. So if you think that might be you and you just want to be done with the stress of the class and you don't, I mean, I'm sure taking that 3-hour test or however long you took, I bet that wasn't a fun time for you guys, right? So if you want to wiggle out of it, if you're willing to double your midterm grade, then I'm totally down for that. I'd like to get a sense of who would like to take the final, because I don't want to be spending 3 days of work if nobody's going to want to take the final. You know what I mean? So if you're a person who thinks you might like to try your hand at the final, please let me know. I suspect it'll be such a small number of people that even if I don't finish putting all the questions in, I can just give you the paper version and then grade that. We'll figure that out. So anyone who wants to take the final has the right to take the final. There is a final for you, and you can take that. It will be on all this stuff, which you can see is a little bit complicated, right? If you'd like to wiggle out of that, I'll give you an opportunity to do that, okay? And that means we can just kind of have fun and do some homeworks and labs together and think about stuff and bullshit. And that's the way a class should be. It should be kind of fun to learn about stuff. So keep those things in mind going forward. I still have a lot of grading to do. I'm going to work on it. I'm just chipping away at it. Give me some time, okay? Okay, guys, I'll see you on Thursday. Take care. Vladimir, I'll stop the recording, but I'll stick around so we can talk.